Yes, we can.
Okay. Okay, maybe I will share the screen and let's start talking about it. So welcome everybody. This is the real-time operating systems lecture. Uh, Today there will be a little bit, let's say, there will be much details about the organization of the whole event, whole lecture. We'll be having a little bit of information also regarding the operating systems and so on. But maybe you already know this is kind of my tradition coming from one of the professors from the university that the first lecture is shorter, usually due to the fact that everybody are warming up during the semester. So about this course is ending with exam. This is quite obvious. We should take it into account. And participation in lectures is generally recommended. You already know it from the AISV lectures that there will be short tests, and this is the possibility not to write an exam if you pass with 75% of the positive points from the short test. And as you know from the AICV, normally I'm not putting too much details into the lecture notes. So this is your job to do it during the presentation. So this is also the another point in which the participation is really recommended. But it's not the way that you have to be. So basically, this is only the recommendation. I think the recommendation, which is saying by itself that, yeah, this is a nice to do thing. Yeah, there will be a project, and we have already met. I think both groups has already met within the projects. And from my perspective, the project is more important here. So this is the reason why I'm putting 60% of the grade for the project and the 40% grade from the lecture. This is the typical, very practical subject, I think, and it should be in that way. About the project, the project for both groups or generally projects in this course is, I would like to say, 2 stages. We have 2 stages. And one stage is using the PC computers. And first of all, we are somehow getting to know the POSIX standard. So we are just using the normal Linux. Then we are switching to the Xenomai. And in the Xenomai, uh, we are getting to know a kind of the operating system which is compliant with some elements of the POSIX, but in general, this is the real-time operating system. And the idea is to show, for example, that for the real-time operating systems and normal systems, there is a big amount of the shared resources or the shared the same things, practically speaking. And there are some little differences in theory, but in the practical way, the differences are very countable here. And this is what makes the difference between the RTOS and the normal operating systems. So this is about the first stage, and the second stage is about usage of free RTOS. And this is that thing in which you are going to present or to do a real project. So basically using some kind of the approach which can be found in the industry, you are going to design a product. I will be a kind of the buyer or the product owner, whatever you mean here, and I will be trying to get some kind of the thing, and you are going to provide it to me using some kind of the standardized way to do it. And this is that real part in which you are doing that project. In that first stage, you are doing somehow also that project, but this is more closely, I think, to the laboratories or something like that, because this is more structurized and this is not so general. But I think this is the way it should be done in this subject due to the fact some details, and basically whenever I will be just saying in the very beginning of the project, just do that project of that embedded device, it will be problematic and it will be not straightforward. So basically some kind of the things has to be get known before starting the project. About the program, so first of all, we will go into the introduction of the RT systems, then the systems overview about the PC and microcontroller, so totally embedded, RTOS system services, thread synchronization timers, frankly speaking, for the open operating systems also, the scheduler, Xenomai RT system. Xenomai, this is the distribution of the, we can say with the mental shortcut that the Xenomai is a kind of the distribution of the real-time operating system based on Linux, but it's not full true. We'll see why. There will be talking about the kernel space and the real-time driver model, free RTOS, interruptions, peripheral devices, real-time communication protocols. So this is about what we are going to do and what we are going to talk. Basically, I'm really introducing very much about the things like the threads processes, mutex, semaphores, synchronization of the thread, synchronization of the processes, and so on and so on, because for it doesn't matter whether we have the RTOS system or just a simple Linux system. For both operating system, all of that stuff is working, but the differences are a little bit small, and you will be able, I think, easily to see them. So basically, this is why we are also talking about that not real-time operating systems here, because we are making some bases. Okay, so this is about the program. Maybe some kind of the details about the things like the something which is called Krajowe Ramy Kwalifikacji, so national frames of qualification. I don't know whether this is a nice translation. So after this course, you should be able to design the RTOS application is given RTOS system. It might be the Xenomai or the special version of the Linux or the free RTOS or the QNX. So you'll be able to make it in general way. So for example, think about some details like the priorities and this communication between the threads, depending on the needs. This is one thing. You will know for sure what is the real-time operating system. This is the thing which I'm really strongly, let's say, putting effort for you to know, because I will say in a moment why. You will also know all that services which are in the RTOS and normal operating systems, and all that possibilities we can have and applications for example, of the RTOS systems and other systems. About the consultations, I'm not, let's say, right now putting any dates about the consultations. As far as I get, 50% of the consultations has to be stationary mode. So I'll be putting some kind of the information where you can find me into 109A C3. So this is my typical room. But I think that nowadays using the remote sessions and the online method of the communication is really working. And this is also the method for getting me in touch. So basically write me the Microsoft Teams. Don't write the email, because this is that problem that I'm not normally using the emails because too many informations are coming there and I'm just losing some kind of informations from the students. So basically, this is Microsoft Teams gives me the possibility to have a short and fast interaction with the people, the man I would like to write something. So basically, please write me on the Microsoft Teams as we did it before. About the normal thing with me, this is that thing that whenever I'm not answering within, I don't know, 4 hours, one day, just send me once again the note or ping pong or something like that, because probably I have read it and you will be able to see it in the Microsoft Teams that I have read something, but I haven't answered because due to different reasons. For example, I have seen it on my cell phone that you have written to me anything, and the answering will be too long on the on the cell phone, and after getting to the computer I don't remember that somebody asked me about that. So basically this is unfortunately my disadvantage, but yeah, I think that together we can handle it in that way. So once again, whenever I'm not answering, please repeat your question, repeat your information message, and so on. And I'm not really getting angry or mad about it. This is the typical thing with me. uh, okay, this is it about the consultations. I'm thinking what's more about the methods of, let's say, what we are going to use. First of all, we are going to use the portal, okay, as we did it previously. And the portal, I will be placing the materials. I will be also placing materials in our Microsoft Teams channel. So I would like to use it more efficiently than portal only for the evaluation processes. So basically for putting the grades and so on. There will be short tests. We'll see how it will be working during the normal sessions on the university, how we'll handle it. Normally, I did it in that way previously, this course before the remote sessions started. I did it in that way that people has just written in the piece of paper such information that you were normally putting in the e-portal. So this is a little bit tricky because sometimes it's not easy to write something or detect what somebody has written there, but we will see. And so this is it. And yeah, about the lecture notes, I will be putting with some with some additional time for you to prepare it and so on for the lectures. And I think that's all. Do you have any questions? Yeah, I've been talking too much.
I wanted to ask
Yeah.
whether after 14th lecture will still be online or it will be stationary again.
Yeah, regarding the dean's decision, it should be stationary, but from my perspective, for example, it will be better for me to make it still remote. But it's generally, I will ask your senior student, what do you think about it? And maybe we can just ask, I don't know what are your, let's say, situation after, for example, this lecture, whether you have that lectures on the university or not. We can just try to communicate within this aspect. But right now, it looks like after 2 first weeks of the semester, we should get back to university. But as I said, I think it depends, and we can somehow influence that decision or make some changes there. I hope.
Yeah, I mean, yeah, it will be nice to have it remote, according to my perspective, I guess.
Another questions? And of course, whenever we will be making the remote sessions, I will be recording that of course that lectures also. Okay, so let's go to the things regarding the operating systems, or let's say the definitions about the things we will have to discuss it. Subject of my, let's say, lecture notes will be
So
first.
are you
Yeah.
going to record today's lecture?
Not really, because this is only the beginning, and I think on the next lecture I will be making some repetitions, so it will be there.
Okay.
Right now, I'm just only wanting to, let's say, draft a general scheme of everything and just put some introduction information to your head and to easy get what I'm saying in the next weeks. So this is that. But as I said, I will be making some repetitions next week. Mm, a subject of my lecture, or that thing I'm going to focus on, is on embedded systems. So we are going to talk about that systems that are, let's say, transparent for us. Embedded system, this is the special part of the, or let's say this is the special thing, because from the embedded system you only want one thing, that it's working and it's not giving any problems with that. So basically, you even don't know that there is some kind of the embedded system working, because your services that it provides there are for you, and so a little bit transparent from that perspective, from your perspective. So basically, imagine that right now we want to make that embedded system, put it, I don't know, in the shelf of our, I don't know, wardrobe, and don't remember about it for a long, long time. For example, I don't know, maybe you know, wait a moment. I will show you. This is a little bit humorous project, but maybe you know that project which is called Szklarnia, PWR Szklarnia. So this is the embedded system which is generally put in the C13 building, and C13 building is having a big number of windows. So from the perspective of the temperature, it is getting very, very high, as you can see, for example. And this is a quite big, maybe not quite big, but quite fun project. But as you, for example, will read some information, this is the project in which the designer created ESP32 application. Maybe there should be some pictures. Yeah, these are the pictures of that embedded system, and that general embedded system, that general thing has been put somewhere in the C13. There are special, if you go there under the sailing, there are some special, maybe not the pipes, but the paths, technical paths in which there are cables, pipes, and so on and so on. Probably somewhere there it has been placed. There is a small battery, and that small battery gives you possibility to use that embedded system for 4 weeks. So for example, once per month, that designer has to go there and change the battery. So this is the real essence of the embedded system. So embedded system is something which is working totally transparent for us. We do not see any, let's say, obvious operation of that. We are using some kind of the services, for example, monitoring of the temperature, or the garden watering systems, or something like that. And that's it from the perspective of the user. Nothing more is visible. And this is the reason why the embedded system has to be robust from this perspective. So basically, we cannot have such situation that our application, which is working there, it doesn't make any difference whether we are talking about the bare metal application or the just operating system application is failing somehow from the perspective of the execution. For example, segmentation fault or something like that. It's not possible to have a nice embedded system with such problems. Or from the perspective of the memory management, it's not possible to have the embedded system with the memory leak problem. So basically that we are getting much more the amount of the needed memory from the perspective of the dynamic allocation due to some, let's say, bugs in the code is increasing within the time, and after some time we are not having any more free memory, and we have a collapsed our system. So this is the idea of the embedded system. And the nice, let's say, placement of such embedded system is our cars. Okay, so automotive market. So I don't know whether you know, but currently in the cars we have something like the 70 to 100 embedded systems. For example, the controlling on of the mirrors, that side mirrors is done using the single embedded system. For example, in the, let's say, maybe not the normal, but classical cars. One moment. I'm saying classical cars because everything has changed whenever the Tesla came into the market. Because before there was a statement of the manufacturers of the cars that the different individual systems of cars should be made using the microcontrollers should be standalone, and from that perspective, we ended with that 100 embedded systems. Tesla came into the market and said, this is the thing which is not good because we are losing some kind of the performance, we are needing much power management. From that perspective, and maybe it's better to make, I don't know, 5 computers inside, but very powerful, and let's say virtually somehow divide the resources. So basically the two different approaches to the same problem, and we can see that right now that development of the Tesla ideas is quite easy and efficient from the perspective of the classical cars. Sorry. So basically, first of all, I will be talking about the embedded devices, and I will be much more talking about the automotive market, and it will be also visible in the next 5 minutes, I think, within next minutes. Generally, the question is, what is the operating system? Because real-time operating systems, okay? Real-time, we will say about it next, but first of all, operating system. This is a kind of the abstraction over the hardware. So basically, imagine right now that we have the computer and we have that Windows and or the Linux. And from that perspective, we are writing the application, and the application is how communicating with the user. Okay, so we have the single points of interactions between that different layers, and the user, from its perspective, doesn't want to know anything about, for example, the hardware, about the CPU or something like that. He enters the KFC and he wants to order the chickens for lunch. Okay, so he wants to put some I don't know, go to that automated site and check some boxes and get some food. So this is what the user would really want. And this everything operating system, hardware, and all that thing are hidden after the application. So we are preparing some kind of the layers in order not to maybe show too much, but this is that from the perspective user, he doesn't really want to know it, what's happening, and this is not needed for him. And yeah, from that perspective, it's better to make such layers. So user communicates with the application, then the application communicates with the user, and the application communicates with the operating system, while the operating system is communicating with the hardware and application. The hardware is only communicating with operating system. So from the perspective of the abstractions, the operating system hides the hardware inside. This is a nice thing because when we are developers, we don't want to know what are the details about the hardware. We just want to get a slip for 1 second in our application, or just to read the value of the analog to digital converter in expressed in volts, not the number of the bits or the values of the bits, and we still have to know what is the resolution, what was the reference voltage, and so on and so on. We just want to have a voltage, nothing more. Okay, so for example, for the battery management system, we want to only ask our let's say operating system what is the, let's say, current current voltage of the battery, and that's it. So basically, this is a nice thing from the perspective of the designers of the applications, from the perspective of the users, to have the operating system as an abstraction layer over the hardware. There is another tricky, maybe not the tricky, but it's another part of the history that we can imagine that, for example, hardware which is doing the same thing, which is doing the very basic hardware with the sophisticated software. So basically, when we are creating a robot, imagine right now, in the, I don't know, 70s, 60s, 50s, there were an analog robots. So basically that robots were doing some kind of the things that maybe not were autonomous, but automated. And they were using only the hardware solution. So you can easily imagine the such robot even now, that robot that interacts with the light or follows the light. So basically what we only need, we have to get some detector of the light, for example, sensor transistor, phototransistor, okay? And that phototransistor has to somehow control the engine. So somehow has to control the other transistors with some kind of the logic which will be implemented in the form of the circuits. So some kind of the amplifiers will be needed and so on and so on. But basically, we do not need the software for doing that. Okay. But from that perspective, we are ending with very, very, let's say, sophisticated hardware, which is doing only one thing. Okay. This robot is doing only one thing. And whenever we want to change that, I don't know, that light to some kind of the other thing, for example, I don't know, alcohol sensor. There are some kind of the robots that are moving through, or let's say, following the alcohol path. So this is the something which is imitating the nature and the ants. The ants are leaving the pheromones, and this is the reason why the ants are moving in some kind of the line, because that first one is losing some kind of the pheromones on the path. And this is the same situations we can do with some kind of the alcohol sensor. From that perspective, the changes here might be not so easy to do, because we have to redesign our hardware and so on. And when we introduce something like the software abstraction, so we have a very general hardware and the operating system and the application, or the application over the hardware, because we can imagine such situation. We have the bare metal application, so totally no operating system. And as we are, for example, let's say programming the AVR Arduino or something like that, this is the bare metal applications, for example. Here we are changing only some kind of the details of that application. For example, still we can use the analog to digital converter to get to know, for example, that sensor readings, but maybe the parameters has to be changed due to the fact we has changed the sensors from the phototransistors to that device, or to that sensor which is detecting the alcohol path. So introducing software into the hardware, let's say word, gives the possibility to have not sophisticated, very general hardware, and from the perspective of the manufacturing, easy to be manufactured and easy to correct the bugs system. And then all that thing, all that details and all that very problematic things are covered in the software. And the operating system is another let's say another stage here. So we are not want to still have the same problems. So for example, think about, we want to have the independent from the platform solution. In the AVRs, for example, we have to define some kind of the constants in our application in order to get to know how many ticks of the processor are for the, I don't know, 1 second. In, for example, FreeRTOS, everything is already covered in the operating system. This is quite the same thing, but we do not have to write that. We just have to write some kind of the values of the seconds we need. So nothing more, because it's already covered here. So this is another part in which we are making our life a little bit easier. But there is also some kind of the cost for that, because maybe the using the bare metal application will be faster. I mean, the faster regarding the development, because this is the simple LED blinking, than usage of the free RTOS. So in order to summarize, operating system is a kind of that abstraction layer, which is giving you a possibility to somehow manage the hardware in some reasonable way, and to get some kind of the software resources and services, not thinking about details too much of that hardware. And from that picture, you can see that this element can be somehow easily taken over and, let's say, changed. So basically, we can have the PC here, or we just can have the ARM build, ARM a platform or something like that. And all that stuff should be somehow hidden here in the operating system. So basically, when we are writing the application for the Linux, we don't care what is the hardware, what kind of the laptop we are using, because all that things are covered here in the operating systems, and we have that translation of that different systems here. About the types of the operating systems, we can have a single and multitasking. So basically, once upon a time, some time ago, there was only the CPUs with one cores, and generally we were able to do one operation per single quant of time. Currently, we have multi-threaded, multi-cored CPUs, and we are able to make several things at the same time. And this is the same with the operating system. Operating system can handle single tasks, so one thing in a one time, or several things. But it depends also from the platform, hardware platform. Single and multi-user. So for example, we have the Linux or we have the Windows, then these are the multi-user environments. And single environment, for example, free RTOS, there is no user. So basically we have the single user. Distributed, yeah, this is kind of the mystery for me, but we can imagine that, for example, the operating system gives you some kind of the services, and this is totally known situation that, for example, the print server can be a total different, let's say, hardware unit with the part of the operating system, but from the perspective of you as a kind of the user of the server, this is the transparent thing for you. So basically that operating system distributed means that we can have the distributed services and the distributed hardware from that perspective. And the real time. And what does it mean real time? This means that our hardware and software is subjected to real-time constraints. So basically, this is the tricky part. So system must guarantee some kind of the response within specified time constraints. So this is the thing, as I said before, I already want you to know. So basically, whenever somebody asks you what is the real-time operating system, don't answer that this is the fast system, because the real-time operating system doesn't has to be fast. It can be totally very slow, but it can do one thing, but it's I mean the slow from the perspective of the performance, because still the operating systems and the systems and that computational systems, these are the systems which are working with, I don't know, milliseconds times or microseconds times. So from the perspective of that computer IT world, this might be a very, very slow, but from the perspective of the person, human being, this is kind of the fast system still. But the real-time operating system, this is the system which guarantees the maximum time of the realization of that service. So this is not only one thing which is very important here. So basically, we have the maximum time in which we should get some kind of the response. So it means that basically we can have that response faster, but never later. This is the very important thing. And the live example, airbag system. Imagine right now that airbag system will be a little bit after the delay about the deadline. So the deadline is set, for example, 200 milliseconds after the hitting impact of the something. You have to, let's say, expose that material, and the airbag has to work and has to be inflated and has to cover the face of the person. And imagine that airbag is a little bit delayed here. It's not possible because it may come to the harm or injury of the person or even the death. So from that perspective, there is no time for not guaranteeing that response time. So this is the real nice example of the real-time operating system. Frankly speaking, real-time system. And I'm talking about real-time system because the system is a tricky thing, because that I don't know what is the good definition of the system, because the system can be composed of the systems or subsystems. So basically, you have something like the matryoshka. You know that those which are big doll. In the big doll, there are small dolls, and we are, let's say, recurrency here. We are having the recurrency, and this is that thing with the system. So basically, everything can be a system. So this is that tricky part of the systems. And with that tricky part, with that everything can be a system, when we are talking about the embedded world, the system is the hardware with the software. So basically the hardware platform with the software, because we are talking about the whole product, whole element, whole, let's say, thing which is doing something. So this is from our perspective system. So basically, when we are talking about the real-time system, we are talking about the hardware plus software or the airbag, for example. So we are talking about all that microcontrollers, all that elements, all that actuators, sensors, and so on, and also about the software. So all that stuff has to be guaranteed some kind of the response within specified time constraints. So this is it. About the classification. The classification is quite easy. There is a soft, firm, and hard, and the problem is always with the firm real-time systems. I will start with the soft. So the usefulness of result degrades after its deadline. There will be degrading the system quality of service. With the generally, when we are creating some kind of the embedded system, we have some kind of the idea what that system should do. So basically, we know what is the highest quality of service. But for example, the car, we can treat as a kind of the system, okay? And we know that the quality of the service of the car is just, let's say we want to drive from one point to another point and so on. We can add some kind of the parameters in the comfortable way and so on and so on. And imagine right now that when we are treating the car as a kind of the system, we are having a problem with the audio. Okay, so from the perspective of that real job we have to do with that car, the problems with the audio does not create any problems. But from the perspective of the system's quality of service, it's a little bit degrading here. So we have the degradation, so in decreasing the level of comfort here, or the level of the quality of the result, let's say. So basically, traveling in silence is not very funny, and this is the reason from our perspective. But this is something like the finite state machine. So please imagine that we have that quality of service with that highest rank. There might be a smaller quality of service ranks, so basically some kind of the degradations of the systems, but the general idea of the system is still provided. And of course, there should be something like the state, which is describing the total failure or the partial failure of our system and so on. So these are the things about the state representation of the system, let's say. And from the perspective of the soft real-time operating system, whenever we are dropping regarding the quality of service, so we are a little bit degrading regarding the quality of answer, we are having the soft, and it is allowed, we are having the soft real system. The firm real-time system, this is quite similar to the soft real-time operating system, or the soft real-time system. But here we have a little bit, let's say, bounded that idea. So we have to have infrequent deadline misses. So infrequent quality of service degradation. And from the perspective of usefulness of that idea, the results after that time will be equal to 0. So basically, it's not a big harm for our system, but we lost some kind of the time, some kind of the power because we made some computations. So imagine right now that we are making some computations about the path, and for example, it took us a little bit long time, and from time to time because we have some problems, but we are doing that computations within some horizon. So imagine that right now the first, I don't know, several meters are okay, and we have that, let's say, deadline misses of the computations for that longer, let's say, longer horizon. So for example, I don't know, in the 100 meters, and we are, let's say, traveling with the small velocity. So from that our perspective, it doesn't make any harm to us, but the usefulness of that data, usefulness of that computations is equal to 0, because in that given moment we have already traveled some kind of the path, and currently that path is not valid anymore. So from that perspective, we can just put it into the trash. And the most important, hard real-time systems. So this is the system in which missing a deadline is a total system failure. So there is no degradation. There is already binary operations. So system is working or not working. And such example is the airbag system, for example. So missing a deadline of, let's say, coming from the state or let's say waiting for action to the ready is and having some kind of the missing deadline here is a failure for our system because somebody can be hurt. And from the perspective of that classification, I really like a little bit different classification, not so Wikipedia like. The classification goes in that way that the soft real-time systems, or just soft and firm, these are the real-time systems in which not fulfilling the deadlines will be, let's say, affecting in loss of money at maximum loss of money, not loss of life or the health of the person. So basically, we are losing money, nothing more. And from that perspective, it's harmful somehow for us, but still better than losing the life. And the hard real-time systems, these are the systems in which the missing deadline is equal to the injury of the person or even the death. So these are the, I think, the nice classification of the real-time systems. And this is the self-describing classification here. Yeah. And basically, this is everything what I wanted to say today about the real-time systems. And yeah, do you have any questions? It looks, yeah, please go. I think not yet. Normally, I'm putting the test, let's say that the trial test in the second lecture, but you already know that short test is and the idea of the short test is. So basically, we'll be not putting that short test next lectures.
I have a question about the long-term operation of the embedded systems. Is there some solution for memory fragmentation?
Yeah. So basically, with the memory fragmentation, first of all, memory fragmentation comes from the idea that we are making the dynamic memory allocation. And the embedded systems, especially that real-time systems, are saying one thing: do not make the dynamic memory allocation. So no pointers, no such things, no creating the objects in the runtime and so on. So this is one thing which is, let's say, used by industry in that way. Another part, for example, in the free RTOS, you have some kind of the strategies about management of the memory. And that strategy of the management memory gives you the possibility to not have the fragmentation too much, but the fragmentation is still the problem. The last possible, I think, and this is the thing which is happening, frankly speaking, from time to time, for the memory fragmentation of the embedded system is just the restart of the embedded system, because when you are restarting, everything starts from the very beginning. But here you have to somehow, whenever this should be somehow some kind of continuation of the service, you have to somehow, let's say, save the state into the some kind of the flash memory, and then has to read during the startup. And maybe this is a kind of the thing which is a little bit, maybe sounds a little bit crazy, that you have to restart. For example, we cannot imagine that the airbag will be restarting during the car movement. But for example, there might be in the lifetime of your embedded system such points in which the restarting will be possible. For example, when we have the fridge, it's not a big harm to restart the system of the fridge in the night, because 99% of the people at, I don't know, 3, 4 o'clock in the night will be just sleeping. And from the perspective of the fridge, it doesn't create any harm, because from the perspective of that, let's say, physical changes in the gases and so on, we will not see it. From the perspective of the airbags or the cars, as I said, in the cars, for example, the dynamic memory allocation in such critical system is just not allowed. But for example, maybe you don't know, but our cars are living even we are not driving them, because they are still supplied with the power and they are still waiting for something. And for example, for such system, the moment in which the car is not used but just, let's say, staying in the parking line, maybe that option in which the restart of the system is quite a nice option to be done. Because when we are talking about the embedded system, the rising up the embedded system, even with the sophisticated software, it shouldn't take too long. I mean that I think it should be somehow maximum value of the time needed for the PC computer with the Linux to be rising up. So something like that. So there are plenty of the options. You will always hear about whenever you say the embedded systems, and especially critical embedded systems, or that systems are going to work with the person, that you are not allowed to do dynamic memory allocation. But as I said, there are many things with such problem of the fragmentation of the memory. There is also another thing I will be saying, I think, in the next lecture, that you can create your own memory allocation mechanism. Okay, make a memory pool. So basically, in the very beginning, allocate a big number of the memory portions. Imagine right now, I know you can just simulate what number of will be needed for you, and then somehow manage it. So from the perspective, somehow make that refragmentation, or let's say leaving the memory, or just another strategy for doing that is not having a constant value of memory chunks to be allocated. So basically, every time we are allocating 4 bytes, for example. So basically, we'll be not having any problem that whenever we have the free part of the memory, but we are not able to put anything there because it's not enough. So there are plenty of the options and the plenty of things, and depends on your application. And maybe, yeah, that's it.
Okay, thank you.
Okay, so thank you very much for being today. I will put that presentation, because this is a very important presentation from the perspective of the rules, and also write that information about the short test and possibility not to write the short test, and that threshold we have to follow into the Microsoft Teams, and I think in the portal in some kind of the near future time. Okay, so thank you very much. I wish you a very nice day. Bye.
Bye.
Thank you. Goodbye.
Thank you.
Thank you. Goodbye.